Welcome to this second example of a DC network. And in the previous video, we looked at how we could use several of the concepts that we've covered so far in tackling a more complicated problem in the form of a DC network. And in the last example, we actually used Kirchhoff's current law, we used the idea of parallel resistors, and we used Ohm's law together to try and work out the different currents and voltages in a given DC network. We're going to do something similar with this example, but rather than using Kirchhoff's current law and the current divider rule, we're actually going to use Kirchhoff's voltage law and the voltage divider rule, and hopefully work out the currents and voltages in each of these resistors. So, to begin, much like we did in the last video, we're going to try and simplify this circuit a little bit because we can make our lives a little bit easier, hopefully, by simplifying this network into something that's a little bit more manageable. So first of all, we have some resistors here that are series elements and some that are in parallel. And we're going to do our best to try and reduce this circuit down as best we can using series and parallel resistors. Again, like I said in the previous video, if the idea of series and parallel resistors is unfamiliar to you, or if you need to brush up on Kirchhoff's current law or Kirchhoff's voltage law, I would recommend going back to those videos and watching those first before tackling this more complicated problem. So, assuming that we're happy with those concepts, let's have a look at how we can simplify this circuit. First of all, I want to have a look at the series elements in this circuit because we can see here that R2 and R3 are both in series. And likewise, we can see that R4 and R5 are in series. And so the first thing I want to do is simplify this circuit by adding those two series elements together to get total resistors. So when we do that, we should see something that looks a bit more like this. As you can see, the 330 ohm resistor and the 390 ohm resistor that were on the top there have added together to make 720 ohms. And the 470 and the 560 ohm resistors on the bottom have added together to form a total resistance of 1030 ohms. Now, I want to keep my notation consistent here. Those two resistors on the top were R2 and R3, and so I'm going to call my new resistor here R23. That's just to remind me what's going on in this circuit. And likewise, R4 and R5 were on the bottom. Added together, I'm going to call that resistance R45. We can simplify this circuit further though, because now we have two resistors in parallel. We have 720 ohms and 1030 ohms, and we've covered how to add or combine resistors in parallel by using the parallel resistor formula, which looked like this. It was 1 over RT equals 1 over R1 plus 1 over R2. But in our previous DC network example, we actually talked about an alternative formula that we could use, providing that we only have two resistances in parallel. And that formula looked like this. It was RT equals R1 times R2 over R1 plus R2. So in this case, we're going to use this second formula here because it's a little bit easier in this instance. Now, we're talking about R1s and R2s in this formula, but let's be consistent about what it is that we're calculating here. In our case, we're saying that the total resistance, I'm going to call it R2, 3, 4, and 5, because it encompasses all four of those resistors now, is R23 multiplied by R45 over R23 plus R45. And let's plug some numbers into that equation. We'll say that R23 is 720 times by 1030 over 720 plus 1030. And if I calculate that, I get an answer of 423.77 ohms. So now I can simplify this circuit even further. If I remove from my circuit these two separate elements, because we've now combined them together, and we can just put one resistor in its place, and we can say that that one resistance, which I'll draw in here, is, we've calculated to be a value of 423.77 ohms. Finally, we've got two resistors in series. We've got R1, which we haven't really touched yet. It's that 220 ohm resistor on the left there. And now we've got R2, 3, 4, 5. We've got all four of those resistors combined into one. So the last thing I can say is I can add those two resistances together. We can remove all of this, and we can say finally that our total resistance, which I'll call RT, is just one resistor, which I'll draw in here. And we can say that RT is a total of 643.77 ohms. Finally, what I can do is I can work out the supply current in this instance. So the current that emerges from our battery and goes around the whole circuit, this is the supply current, and we can use Ohm's law to work that out. We can say that IS is voltage divided by resistance, and in this case the voltage is 10 volts, divided by a resistance of 643.77 ohms. And by calculating that, I get a supply current of 0.01553, or we can multiply that by 1,000, which makes it a little bit more manageable. It's 15.53 milliamps, because I've multiplied by 1,000 there. So let's return to our original diagram here, because we now know a few things about this circuit. We can say first of all that our supply current is 15.53 milliamps. And now what we're going to try and do is we're going to try and work out some of the different voltages in this circuit. Now we could do this many different ways. We could do it like we did in the last example. We could use the current divider rule. We're actually not going to do that here. We're going to try and use a different method. We're going to use the voltage divider rule, which takes advantage of Kirchhoff's voltage law. Now, there's no right or wrong way to go about this question. I could easily do it using Kirchhoff's current law, but we're going to try it a different way. So to begin with, let's have a look again at our circuit here, because we've made some simplifications to this circuit and we've already tried to make it so that it's a little bit more easier to manage. Let's go back to what we had just a second ago, because we said, if you remember, that this whole resistance here could be simplified down to just one resistance, which we called R2345, and we said that was 423.77 ohms. So what we can do now is we can use Kirchhoff's voltage law, which says that the sum of the voltages dropped in the circuit is equal to the supply voltage. Now we applied that by using the voltage divider rule, or something called the potential divider rule. Now, again, if this is something that you're not sure about, I would recommend going back to that video. But we're going to put it into practice here, because that 10 volt supply is actually going to split into two voltages. We're going to get V1, which is the voltage that we measure across R1. And we're going to get what I'll call V2345, which is the voltage that we measure across the other resistance there, R2345. And to do that, we're going to use the voltage divider rule, or the potential divider rule. And if you remember, the way we set that up is we say, let's look at V1 first of all. We say V1 is equal to the supply voltage multiplied by a fraction. So in this case, 10 volts multiplied by a fraction. And on the top of the fraction, I put whichever resistance I'm measuring across. So in this case, V1 is measured across the 220 ohm resistor. So I'm going to put 220 on the top. And on the bottom, I put both resistances added together, 220 plus 423.77. And if I calculate that, I get an answer of 3.42 volts. So 3.42 is the voltage that we're measuring across V1. Now, a clever bit of subtraction here, because we can easily determine the other voltage, V2345, because Kirchhoff's voltage law says that both of those voltages, V1 and V2345, should both add up to 10. So the remainder must be the other V2345. So simply saying 10 minus 3.42 is going to give me V2345, which in this case is 6.58 volts. So now we've gone some way to breaking this supply voltage down into two smaller voltages. We can go further though if we return to our original diagram. So now we can say, first of all, we know that again V1, the voltage across this one resistor here, is 3.42 volts. And we can say that the voltage across, if you can imagine a voltmeter V2345, measuring across this whole section of the network here, we can say that that voltage is the other voltage that we calculated, 6.58 volts. Now what we're going to try and do is we're going to try and focus on this right hand section here, because we can actually break these voltages down further, and I'm hoping to break that 6.58 volts down into 4 even smaller voltages by using the potential divider rule again. So let's first of all concentrate on this top row here, where we've got R2 and R3 in series. What we'll actually find, and what we saw in the previous video, is that parallel resistances share the same voltage. So R2 and R3 will get that voltage of 6.58 across them, but R4 and R5, because they're in parallel, will also get the same 6.58 volts across those as well. And what we're going to do is we're going to use this to our advantage. Let's return to the original diagram here and use the potential divider rule again, because R2 and R3 are a potential divider in themselves. And what we can do is we can measure V2, which is across R2, and we can measure V3, which is across R3. And we're going to use the same potential divider rule to do that. So let's set this up for V2 in this instance. We can say that V2, again using the potential divider rule, is equal to the voltage applied to this network, which in this case was that V2345. That's the voltage across this whole section of the network. So V2 is equal to that 6.58 volts that we calculated before, multiplied by a fraction. And on the top of that fraction, because I'm measuring across V2, I want to put R2, which in this case is 330. On the bottom, I put both resistors in that series element added together, 330 plus 390. And if I do that, I calculate a voltage there of 3.02 volts. Again, we can do a little bit of subtraction here, because V3 must be what remains of that 6.58 volt supply. So we can simply say that V3 is equal to 6.58 minus 3.02, which gives me an answer of 3.56 volts. We can do the same thing again here for the bottom two voltages, because we can also work out V4, which is the voltage across R4, and we can work out V5, the voltage across R5, and we can use the same method to do this. So again, V4 and V5, they're part of that same network that has 6.58 volts across them, and so we can set up the potential divider rule in a very similar way. We can say that V4 is equal to 6.58 multiplied by a fraction. And again, on the top of that fraction, I must put the resistor that I'm measuring across. So V4 is measured across 470. And on the bottom of that fraction, I put both resistors in my potential divider, R4 and R5, added together. So 470 plus 560. And that gives me an answer of 3 volts, pretty much exactly. So 3.00 volts. And so finally, we can also work out V5 using that same subtraction. We can say 6.58 minus 3, whatever's left over must be V5. So in this case, V5 is 3.58 volts. We're now in the position where we know the voltage across each of our resistors, because if you remember on the last slide, we also calculated V1, which was 3.42 volts. So we now know all 5 voltages across all 5 resistors. And so the last thing we can do is we can calculate 5 currents. And to do that, we're just going to use Ohm's Law. And again, try and set up, much like we did in the last example, 5 equations using Ohm's Law each time. We're going to calculate this time 5 currents. And so let's set this up in the form I equals V over R. And in this case, it's going to be I1, the current going through R1. We're going to calculate I2, I3, I4, and I5. And hopefully we'll notice some interesting patterns when we calculate these. So let's get back to my equation. I1 is going to be V1 over R1. And if I calculate V1 over R1, or rather if I put the values in my equation here, V1 we said was 3.42 over R1, which we said was 220. I'll get an answer of 0.01554 amps. Now, that's not a very easy number to get a grip on. Much better would be to multiply it by a factor of 1,000 so that we can express it in milliamps. So 0.01554 amps is the same as saying 15.54 milliamps. And we're going to do the same thing for each of our resistors. I2 is going to be V2 divided by R2. I3 is going to be V3 divided by R3, and so on and so forth. So let's have a go at each of these. I2, we can say V2 over R2. And so V2 was 3.02, if you remember, divided by R2, which in this case is 330. I get an answer of 0.0091, or better yet, we can say 9.1 milliamps. I3 is V3 divided by R3, and V3 was 3.56 divided by R3, which is 390. And here I get an answer of 0.0091 again. 0.0091 amps is 9.1 milliamps. Now, notice a similarity here between these two currents. And the reason being because we would expect them to be the same. I2 is the current that flows through R2 and then continues to flow through R3. So I would expect those two currents to be the same, but in this case the maths, the Ohm's law, proves it in this instance. Finally, we'll work out I4 and I5, and again I would expect them to be the same, but let's just make sure. So I4 is V4, which we calculated on the previous slide to be 3 volts, divided by R4, which is 470, and this gives me an answer of 0.0064 amps, or better yet, 6.4 milliamps. And I5, the last one, is V5. We calculated that to be 3.58 divided by R5, which we said is 560, and that also gives me an answer of 6.4 milliamps. And again, we're seeing that same current for I4 and I5, which we would expect because they are the same current. They're going through that whole section of the network there. So again, I hope this has been a useful example of how we can apply some of the rules and laws that we've looked at previously to a more complicated DC network. We've looked at using Kirchhoff's voltage law and the voltage divider rule, or the potential divider rule. We've used some series and parallel resistors. And we've also used a bit of Ohm's law at the end to calculate some of the currents in this network.